architecture, a star-like polymer with a thermosetting matrix, so which can be polyamide, epoxyamine resin. So the application is in microelectronics, where we use insulating materials, so with a low dielectric constant. A typical example is the development of new films, thermostable films and opposed thermostable films based on polysaccharides. Polysaccharides are this kind of polymers here, which we use in the laboratory because they have a large range of interesting properties. They have a high dimensional stability. They have a high thermal stability. The decomposition is higher than 400 degrees. They have a high TG. They have a low dielectric constant, low water absorption, and they are resistant to chemicals and corrosive agents. So we developed several approaches to generate nanoporous thermostable PCNs. As you can see in this same picture, the very tiny pores in the films. And they can be used for permeability at high temperature or for nano ultrafiltration. So we developed 3 complementary approaches. The first one was based on the use of a high temperature solvent, high boiling temperature solvent, so as a purging agent like DMP or DBP, dimethyl phthalate or dibutyl phthalate. In the presence, DCB is the monomer. When we polymerize DCB, we obtain polysaccharide. So we obtain this network in the presence of the solvent. And then we extract the solvent by washing with acetone, and we generate the pores. The second approach is based on the copolymerization of the monomer with polycaprolactone. The polycaprolactone will be incorporated in the network, and then by hydrolysis, polycaprolactone is a polyester, it can be selectively degraded and generate pores. And the last one is the trackage technique, which is particularly appropriate for membranes, thin membranes, because you irradiate with high energy particles, you create latent tracks, and these tracks can be can generate pores by a chemical etching reaction. So and by this way, we generate this kind of nano pores that are well distributed in the film. Okay, the last approach to generate porous materials with controlled porosity is the use of semi-IPNs or IPNs. Semi-IPNs means semi-interpenetrating polymer networks. IPNs, interpenetrating polymer networks. So a semi-IPN is constituted of an uncross-linked polymer in blue, which is entangled in a subnetwork in red, so a cross-linked polymer. And an IPN is constituted of 2 networks entangled one with each other. So the idea is if you start from semi-IPNs, if you do an extraction, so a physical washing, you will remove the uncross-linked polymer and you will end up with a porous network. And if you start by an IPN, you need to degrade selectively one subnetwork. So in this case, by a chemical reaction. So you will degrade the blue subnetwork and you will generate the red porous network. So first, let's see an example by using semi-IPN. So here we have this semi-IPN generated by the copolymerization of lactide and caprolactam. So in the presence of hydroxyethyl methacrylate, ethylene glycol dimethacrylate, we will generate a network, a polyidoxyethyl methacrylate network with the polylactate caprolactam entangled in the network. And if you do an extraction, you have blue oligomer, you will remove the oligomer and you will create a porous polyidoxyethyl methacrylate network. Or you can also hydrolyze in physiological conditions the polylactate caprolactam at pH 37 degrees to generate a porous network. Okay, another example is a semi-IPN constituted of a polyurethane network and a linear polysaccharide. So here in this case, if you remove by extraction in DMF the polysaccharide at room temperature, you will generate a porous polyurethane. Depending on the composition of the polysaccharide, if you have a low polysaccharide content, you will have close porosity. If you have a high polysaccharide content, you will have interconnected pores. Another example is the suspension polymerization of divinylbenzene. So divinylbenzene is a difunctional monomer, so you can cross-link you can generate a network just by homopolymerization of DVB. And in the presence of toluene and oligomers acting as coporogen, for example, polypropylene oxide or polydimethylsiloxane, we will generate porous polydivinylbenzene with varying porosity depending on the composition of the toluene or the oligomers. So if you have 100% of toluene, you will have macropores. If you have 100% of polydimethylsiloxane, you will have 100% of macropores. So why? Because toluene is very close, the nature is close to styrene. So as I said initially, you will have a good compatibility, so you will have a small pores and a high specific surface area. And PDMS and polydivinylbenzene, which is typically polystyrene, which is basically polystyrene, the compatibility is low, so you have a low specific surface area. And then when you have intermediate composition, you will have intermediate situations. So you can vary the porosity by varying the nature of the porogen. So this is relatively the same conclusions as we also we already mentioned when we talk about the porogenic solvent. So now let's see how we can get access to porous networks from oligoester-based semi-IPNs. So here in this case, we copolymerize methyl methacrylate with a dimethacrylate. Here we generated a semi-IPN in the presence of oligoesters, so PLA oligoesters. And we remove the oligoester by extraction. Saltlake extraction means that it's with continuous solvent, okay? It's a closed system in continuous solvent. So you wash with a solvent continuously the network, and you remove with a solvent the uncross-link oligoester. You generate the porous PMMA network. So interestingly, we obtain this kind of porous system So when you use polycaprolactone PCL 2000 with BATMA, so with the aromatic here, this cross-linking agent, so you have a very high incompatibility. So when you remove polycaprolactone, you will have a very large, broad pore size distribution and very large pores. When we use PLA, you have a better compatibility between PLA and PMMA, so you decrease the pore size. Then when you change the cross-linker, we use, instead of using this one, we use with urethanes, you will improve the compatibility between the matrix and the oligoester, and we will further decrease the pore size. And eventually, when we decrease the composition of dimethacrylate, we further decrease the pore size. So this is a way to tune the porosity by varying the miscibility degree, the compatibility between the two partners in semi-IPNs. Okay, so in semi-IPNs, you need to vary the compatibility between the uncrosslink partner and the network in order to tune the pore size, the final pore size. So as conclusions, this is a straightforward access to porous or mesoporous network by quantitative extraction of uncrosslink oligoester. We vary the pore size by varying the miscibility of the two partners. So the crosslink have an influence, the composition, the concentration of the crosslink as well. Concerning the oligoester, if we increase the molar mass of oligoester, we will increase the pore size. Of course, I didn't show it here, but this is quite logical. And when we use polycaprolactone instead of PLA, we also increase the pore diameter, because due to an increase of or due to a decrease of the compatibility or the miscibility between the network and the oligomer. So this is an effective and versatile strategy for obtaining mesoporous networks as long as partners are miscible. This is important. So you should find the condition where the partners are highly compatible or miscible. So now let's see how we can obtain porous networks by using IPNs. So just a reminder, IPNs are a unique class of materials in which two polymers are independently cross-linked and entangled. So as shown here, the blue network and the red network. So the advantage is they provide a high dimensional stability. We force the compatibility by cross-linking the two partners. We force the compatibility, and by forcing the compatibility, we reduce the phase domain size. And so eventually, we have a synergy of properties. It means that you may have, it's interesting to combine an hydrophilic network with an hydrophobic, or a soft network and a hard network, or a degradable network and a non-degradable network. And this, we will take advantage of this synergy of properties and these contrasted properties in the same system to generate pores. So by combining a non-degradable network with a degradable network. So these are the methods to synthesize IPNs. Three main methods. The first method is the sequential method. In the sequential method, we first mix homogeneously the monomer or the oligomer with a crosslinker. We polymerize and we obtain a network. Then we swell the network, this first network, with the monomer, the monomer and the crosslink of a second network. And in a third step, we carry out the polymerization and we form the second network. The second method is the simultaneous method. In this method, we mix initially all the components of both networks homogeneously, and then we carry out simultaneously the two polymerizations. So this is a particularly interesting if you have two different polymerization mechanisms, of course. You cannot do this, you cannot apply this method if polymerization 1 and polymerization 2 have the same mechanism, because otherwise they will interfere. So you need to have totally different mechanisms. And the third method, which is actually probably the most interesting one, as it's a combination of the first and the second method, is the in situ sequential method, in which you mix initially all the components of both networks, and then you carry out sequentially the two polymerization. First, the first polymerization to trigger the formation of the first subnetwork, and then the second polymerization to form the second subnetwork and eventually the IPN. So this in situ sequential method you can apply with two different mechanisms or two slightly different mechanisms. So I will generate another link because we will finish in 5 minutes. So yeah, one example here, by using IPNs to generate porous networks. So here we started from this sequential IPN based on polybutyl acrylate and polystyrene. And here what was interesting is that the crosslinks, so the crosslinks are here, what I show here are the red. They are different, they have a different functionality. In blue, they are labile. It means that they can cleaved, they can be degraded by hydrolysis. And in red, they are stable, like divinylbenzene. You cannot degrade in any conditions. So interestingly, if you have a polybutyl acrylate polystyrene, when you degrade polybutyl acrylate, you will obtain a porous polystyrene because you cleaved the crosslinks of acrylic acid anhydride. In contrast, now if you have polybutyl acrylate with divinylbenzene and polystyrene with acrylic acid anhydride, if you do the hydrolysis at room temperature and with basic conditions, you will degrade the polystyrene, but eventually you will not obtain a porous polybutyl acrylate. You will have a non-porous butyl acrylate. And why? Because in fact, you did the reaction at room temperature. It means at a temperature higher than the TG of the polybutyl acrylate. Polybutyl acrylate has a very low TG, -40. So it means that at room temperature is very soft and you have a collapse of the pores. So this shows that you have to be very careful when you do a degradation reaction, and when you want to remove a porogen template, you need to do it at a temperature below the TG of the resulting porous polymer. Okay, so this you have to be careful and take into account that. So into account the mechanical properties of the final polymer. Okay, another example is the use of dioxaline. So by cationic polymerization, you can generate this bis macromonomer, diacryloyl polydioxolane. We can polymerize it to generate a network. In the presence of MMA and the crosslinker, we will do the second network, and we have a sequential IPN, so polydioxolane, poly-MMA. PMMA, polydioxolane, contains eta groups. These eta groups can be cleaved by acidic hydrolysis, so they can be degraded, and in this way, you can generate porous PMMA. A last example is this structure, which I call IPN-like, based on PMMA and polyethylene. So if you irradiate the system with an electron beam, it's a high energy high energy beam, you will degrade PMMA and you will cross-link polyethylene. Because PMMA, as I mentioned before, you can degrade it under UV or under any electron, or also with an electron beam. So this is an interesting